wasn't until the 19th century that things really started to kick into high gear. That's when art historical conservation, as we know it today, began to take shape. The discipline evolved quickly throughout the 20th century, with restoration practices and preferences changing just as quickly. For most of the 20th century, restorers were largely dependent on their own artistry and experience, so there was a lot of different opinions, ideas, and techniques flying around the field. However, in the second half of the century, the field of restoration began to intersect with fields of scientific study, including chemistry. And this really allowed the field to bloom. For the first time, it gave art conservators a way to observe, examine, and analyze paintings, pieces of art, without necessarily disrupting them, disturbing them. A lot of the issues in art conservation are the damage that happens to objects, happens from the inside out, especially with oil painting and other complex chemical materials. So the use of scientific techniques and technology to examine and analyze chemical changes within paintings and artworks without having to take them apart or disturb them was really an incredible change in the field of art conservation. And in the 1990s, this really kicked off with J.J. Boone and his contemporaries when they began to successfully use chemical spectroscopy to analyze changes in the chemical composition of paintings. In the 3 decades since, restoration has become a very intersectional field of artists, scientists, historians, and rather than the sole restorer bearing the responsibility for repairing or ruining an piece of art based on judgment alone, restorers can now work hand in hand with scientists and with analytical technology in order to get a much deeper understanding of their work. Spectroscopy is one of those technologies. It's a way to non-invasively examine a piece for important information, including chemical changes and possible damage to the paint. So this video will not just talk about how revolutionary the incorporation of chemistry and other scientific fields into art conservation practices was. It will also explain or try to explain quite a bit about the drying and chemical process that oil paints go through over time. And it will use, and I'll try to explain to you guys how spectroscopy is used to examine those paintings. It's a really fascinating tool that has led to a lot of incredible discoveries, including J.J. Boone's discovery of metal soaps forming on works of art. So, to begin with, to understand how oil paints degrade, you have to understand how oil paints dry. Oil paint is made up of pigments and a binding oil, most commonly linseed oil. And the drying of oil paint involves several complex chemical processes. Oil paints can take up to several months to fully dry because their drying process involves not the evaporation of water, but the oxidization of the lipids in the oil. Over the course of several months, oxygen molecules from the air form links between the chains of fatty acids in the oil, securing them in place and hardening the surface of the painting. So, for example, think of the oil as a number of small threads. The lipids in the oil are thread-like chains, and as they oxidize, oxygen molecules connect one chain, one thread, to another thread, linking them from simple chains to a cross-hatched, almost woven pattern. This secures the oil in place, and this is the chemical process behind what we physically see happening as the paint dries, the hardening of the surface of the painting. So all of the drying and most of the chemical reactions in the curing stage happen via the solvent, the oil, rather than the pigment of the painting. Pigments, like the ones used in oil paintings, don't bond with their solvents. Dyes do. So a dye, when mixed with water, will bond with the water molecules and fully mix into the solvent. With pigments, the pigments in oil paint don't bond with the compounds in the linseed oil. Rather, they're suspended in the oil. So as the oil hardens through the previously described process, which is called polymerization, the pigments are then trapped in the layers of oil and harden alongside them. So linseed oil is used most commonly as the medium for the painting, but other oils with lots of unsaturated fatty acids can also be used. The reason you need to use oils with majority unsaturated fatty acids versus saturated fatty acids is because unsaturated fatty acids have a double bond in the hydrocarbon chain of between their lipids, which leaves open valence electrons for oxygen to bond with. This oxidization process leads to the formation of crosslinks between the lipids, as mentioned before, and forms permanent bonds that then harden the surface of the painting. So, J.J. Boone described this as the first of three main stages of oil paint development. This first stage is the curing stage, the initial drying period for the painting, in which the links between hydrocarbons are formed. The triglycerides in the linseed oil undergo auto-oxidization to become monomers and then cross-link with each other to form a 3D polymer structure. As links begin to form a structure, the oil paint begins hardening, the top layers of paint stiffening first and the underlayers hardening over the next several weeks. This is why in thick layers of oil paint you can get cracking during the drying process, because the top layer being exposed to more oxygen will oxidize faster than the lower layers of paint, which will continue to shift and move slightly while drying beneath the already solidified top surface, sometimes causing that top surface to crack slightly. However, once the painting is fully dried all the way through, this is what Boone describes as the mature stage. So the mature stage is what we would think of as a finished painting, the completion of the curing stage. In the mature stage, the glycerol ester bonds have been hydrolyzed and a polyanionic polymer has formed. At this point, the bonds that have linked between the hydrocarbon chains have been formed into a solid stationary structure. The surface of the painting is totally hardened and the paint can't move or smear. The metal ions in the pigment. There are metal ions in a number of pigments used in oil paints, which have positive charges. This can be very useful in the mature stage, as that polymer structure that forms between the lipids does have a slight negative charge, and the slight positive charge of the metal ions in the pigment can counterbalance the polymer structure for a more stable chemical reaction. However, in the final stage, the metal-containing pigments can become problematic. Boone's third stage of oil paint evolution is what he calls the degradation stage. It's often not detectable for decades, if not centuries, after the completion of the mature stage. Extensive exposure to light, air, and heavy metals leads to damage and interior degradation of the painting. Common symptoms of damage or interior degradation of oil paint can be paint beginning to chalk or becoming powdery, falling off of the canvas and becoming difficult to clean or maintain without damaging further. This is also the point where those metal pigments, those metal ion containing pigments, can become problematic because those metal ions can begin to migrate over time and form metal soap within the painting through the hydrolysis of water molecules in the air. So, like I mentioned, a number of the pigments for oil painting are traditionally made of metal compounds, usually containing lead, zinc, or cobalt. Lead compounds are also often added to the oil in order to speed up drying time. Metal soaps form through the hydrolysis of these metal molecules. And it works because it breaks down lipids and allows hydrophobic compounds like oil to bond with water. Typically, oil is inherently hydrophobic compound, but when a soap is formed, it acts as a bridge. I mean, that's why we use soap to wash things. They break down oils and allow them to be rinsed away with water. This remains true for metal soaps. As such, when soaps form within a structure made up of oil of fatty acids, the soap will end up pulling off parts of the polymer chain of acids. As it bonds with water that's exposed through hydrolysis of moisture in the air, the soap will also want to bond with a hydrocarbon. And because the soap is more electronegative than the polymer chain, it will then break the polymer chain in order to bond with the monomers within it. As the structure of the polymer is weakened, the metal soaps slowly eat away at the rigidity of the oil lacquer, providing room for the soap to migrate to the surface and allowing the pustules to break through to the surface. This is a particular risk for paintings that have already sustained damage from time and exposure, like small cracks on the surface of the paint, which can happen for two reasons. One I mentioned before, that during the drying process, small cracks, micro cracks can form due to the top layers of paint drying first. And cracks can also form due to unideal conditions or handling over time. These cracks make these metal soaps more dangerous because it provides them a lot more room to migrate around the painting. And the paintings are already weakened, so the damage that migration and the formation of the soap does to the painting is likely to be significantly greater for paintings that are already damaged or weakened. And unfortunately, a lot of old paintings are damaged. Time has always been the greatest enemy of art, and oil paintings suffer damage and degradation from prolonged exposure to air, to light, to mishandling and mistreatments over the years. But still, the work that J.J. Boone did in both presenting spectroscopy in the art conservation world, as well as discovering metal soaps, and another specific tangible thing that conservators can know to look for and fight. He really revolutionized a lot of processes when it comes to working with oil paints. So he came into art conservation as a chemist who was hired to work on some 17th century oil paintings at the Netherlands Institute for Cultural Heritage in the 1990s. And as well as spectroscopy, he used microscopy, energy dispersive X-ray spectroscopy, and Fourier transform infrared spectroscopy to better understand the possible changes to the chemical structure of oil paints after time. And these are all, for the most part, operate via spectroscopy operates by shining a spectrum of lights, a specific frequency of light, on different parts of a painting or object. And depending on the frequency of light that is reflected bouncing off of the object, we can actually use these machines to get an exact formulation of the chemical compound of that exact area of the object. So using this, Boone and scientists since then can travel around the surface of a painting, non-invasively taking samples from every area of the surface and comparing them to each other to see which areas are different from each other, which have changed chemically from their original composition, and what exactly they're dealing with. It's a really, really fascinating discovery. But the question is, now that conservators know about the existence of metal soaps, what can be done to keep them from further damaging the artwork? And that is the tough pill to swallow. Once metal soaps have developed in a painting, we have yet to find a way to permanently remove or reverse them without damaging the painting. They can be cleaned and removed somewhat once they rise to the surface of the painting, but there's no way to reverse or neutralize their development. There's still a lot of factors in the formation of metal soap that conservators are working on figuring out. So it's very possible that we will find a solution someday in the future. But for now, conservators, this has still been really incredible information for conservators to have, as it's allowed them to not only develop theories on what might be causing this and what might stop it, but also come up with preventative tactics, better form new theories and ideas on how to protect and take care of paintings, and try and stop this damage from occurring in the first place. The reality check is that in conservation and restoration, there's really no size-fits-all situation. Each painting is unique and it has its own set of challenges and considerations. And we definitely don't have all the answers just yet, but one thing's for sure, that the incorporation of science and chemistry into the field of art conservation has shown a bright light on the dark corners of the field. So, next time you find yourself lost in the beauty of an oil painting, take a moment to appreciate the incredible journey it's been on. From the artist's brush to the conservator's laboratory, each stroke tells a story. And thanks to the tireless efforts of researchers, artists, and scientists, those stories will continue to be told for generations to come.